I also want to thank my collaborators, Sankey Lee, Robert West, Dongmin Kim, Greg Foltz, Go Salaka, and Hiro Murakami from GFDL. And the talk today is about future changes in extremely active Atlantic hurricane seasons. So a little bit of the overall goal of this research is to investigate what is the relative role between natural variability and anthropogenic climate change with regard to extreme weather events affecting the US. And the specific objective here is to investigate near future changes in interannual variability of Atlantic sea activity in response to a projected increase in the variance of major hurricane drivers. We have a hypothesis here that reads that interannual variability of TC activity will intensify in response to anthropogenic forcing as a result of more extreme swings between large-scale climate modes that drives hurricane activities. So we might expect very extreme hurricane seasons to become more common in the future. A little motivation on why we care about hurricanes and tropical cyclones. Here, TC and hurricanes are interchangeably in this talk, is that they're among the most deadly and costly natural disasters that impact our country each year. And thus the scientific community has placed a great effort in investigating not only their dynamics and their physics in order to improve their predictions, but also to look into their future projections. So what we want to do is actually emphasize more in the Atlantic for this talk. But here in this work from Murakami et al., one of the co-authors of this work here, look at the observed trends in TC activities. And you can see it's very, very inhomogeneous in space. So, but for the Atlantic basin, you see an upward trend where you have positive TC activities for most of the Atlantic basin. So this inhomogeneity does not apply to the Atlantic basin, at least for the observational record, starting in 1980 to 2018. However, there has been many papers on future projections globally as well as for the Atlantic, and this is a very nice paper that encompasses all the work that has been done up to 2020 by Knuckson et al. We show that for the Atlantic basin, and here I just want you to concentrate here on the Atlantic basin, there is a potential reduction in the future of about 15% tropical cyclones per year. That accounts for about 2 TCs per year in the future compared to the current climate. However, most of the previous work regarding hurricane, tropical cyclones, and climate change concentrate on changes in the mean, changes in the track densities, changes in landfalling, for example. So, but this paper in Knuckson really highlights the need to look also at changes in the interannual variability, the year-to-year variability of TC activity into the future, because as you can see here, a 15% reduction in TC activity only accounts for 2 TCs per year, whereas this is much smaller than the interannual variability that we already observed in the 20th century and 21st century. For example, 2005 saw 28 named storms, whereas 2014 only saw 8 named storms, and 2020 saw 30 named storms. So you see these are very large swings in interannual variability already, compared to just a future projection of 2 TC per year change. So that's what we're trying to tackle here, and this is one of the motivation of this work. A little background on what really drives Atlantic hurricane variability on interannual and decadal time scale are the interplay between the Atlantic and Pacific SSTs. So namely, the Atlantic SST here, what I'm showing you here is just a correlation map, and this is from West et al. Paper, which is also one of the co-authors of this work, that show this interplay between warm Atlantic and cold Pacific, mostly over the Colton region, driving enhanced Atlantic TC activities. So We want to really stress this out later in the talk, where we're going to talk about future changes of this interbasing index. And I want to mention that beginning this year, the co-authors here in this work developed a seasonal outlook for Atlantic TC activities, which is now part of the official Climate Prediction Center outlook. So starting this year, our numbers became part of the official outlook that we saw. And it was basically using this interbasing SST index and climate models to build a hybrid model, statistical dynamical model, to basically predict seasonal TC activities. So investigating this SST interannual variability and how it will change in the future will prove to be very important for future projections and to gain our knowledge on how hurricane seasons will present themselves in the future climate. So this is an example of the 2023 this seasonal forecast. So based on the current conditions, we forecast a likelihood of 90% above normal and 10% near normal season and 0% below normal season, with a range of accumulated cyclone energy, which is denoted here by ACE, between 122 and 208. Right now, as of today, the season has been above normal, so we can check mark here that we say like 90% above normal, and that currently there is 145 units of ACE, so right in between our forecast that we did back in May. And these are the number of major hurricanes forecast, 3 to 5. Right now, it has been validated that we had 3. We had 7 hurricanes. We forecast between 7 and 11, and we had, thus far, we had 20 named storms. We forecast 15 to 19. So overall, this interbasing index has proved to be fairly reliable in depicting TC activity. But one of the components of this interbasing index is the Pacific SSTs located over the Colton region. So ENSO, which is the major driver of Pacific SST variability and arguably the major driver of global climate variability, has been shown to be projected to increase in the future its interannual variability, and also has been shown to initiate sooner in the season and grows at a faster pace. So this is just a whole Miller diagram across the Pacific from west to east and in time, 2 years time, a composite of the evolution of El Niños. This is for the 21st century, using both models, 6 future projections and a single model large ensemble simulation, and how this will change in the future. And what we saw that is that there's a faster growth of El Niño in the future, and mostly it resides between July and December, right in the middle of the hurricane season. So the question is, this enhanced future ENSO, how will that manifest when it comes to this interbasing index and future projections of hurricane activities in the Atlantic? Also, this paper by Zhang et al. Showed that the relationship between the Pacific SSTs and the Atlantic SSTs will be enhanced in the future as well, as you can see here by the broadened PDF compared to the 20th century PDFs. So for this work, we will use observational data as well as model projections. For the observational data as a proxy for hurricane activity, seasonal hurricane activity, we will rely on accumulated cyclone energy index, the ACE index, which is defined as the sum of the square of the maximum sustained surface wind speeds and measured every 6 hours. So we're going to use this index accumulated throughout the hurricane season. And that's what you see here plotted on the right. This is the historical ACE index as a function of time. And what you can see is that this has been broken down into 3 epochs: one a high activity era, another one a low activity era, and the later part of the historical period has been an active era as well. So the question is this a global trend or at least a basin-wide trend, or do we see enhanced interannual variability? Because ignoring the first part of the period here before 1970s, before the satellite period, we're going to analyze only the later two parts. You can draw a trend line anywhere here in this graph. So the question is the trend significant? And is it significant compared to the interannual variability? And is the interannual variability also changing or trending upward? Because we can see from this plot that there's more wild swings in the later period compared to the earlier period. This is basically the same plot as before, but simplified. What I did here is, this is just a time series of A's, accumulated cyclone energy, with a linear trend fed to it. And I broken down the two periods, blue, early period, red, recent period. And on the bottom, what I'm showing you is a running variance. So this is a 25-year running variance of the top plot. And as you can see, the running variance also has shown a very nice upward trend where interannual variability has almost doubled compared to the previous period. So the question is, does an active hurricane season like 2005 here, or a very inactive hurricane season like 2014, was that driven by the enhanced variability, or was that driven by the underlying mean trend? We can also see the same pattern if we look at the number of tropical cyclones, and this is all for the Atlantic. We see exactly the same upward trend in the TC count, but also a very nice upward trend in the interannual variability of the TC count. And this is also consistent if we repeat the same analysis for major hurricanes or hurricanes. So how we're going to analyze this? The observational period is very short. There's a lack of enough data to really draw meaningful conclusions when it comes to trends versus internal variability. And also, we have to account for the fact that the observing system hasn't been consistent throughout the year. So we are able to observe more storms now than we were in the 1950s, for example. So the question is that how reliable is this trend, and how can we compare the trend in the mean activity versus the trend in the interannual variability? So what we do is we break down, again, this observational period into two periods, the early and later period, and we draw statistics from them. Since the observing period is very short, what we do is we model thousands, basically we simulate thousands of hurricane seasons for each of these two periods using a Markov model. And this is what I'm showing you here. This looks complicated, but it's not. This is just a Markov model where you have additive noise and multiplicative noise. And the multiplicative noise here is this term here. If you set that to 0, this is just going to turn into a Gaussian model. Very simple model. So we're going to generate thousands of hurricane seasons like the early period and thousands of hurricane seasons like the later period, where we can draw statistics from. And you see in this plot here, this is for A's, historical A's, and historical interannual variability of A's. And on the bottom, these are the probability density functions drawn from the Markov model. These are thousands of hurricane seasons like the one in the early period and like the one in the later period in red. The nice thing about this model is that we can tweak the parameters so that we can generate hurricane seasons like the early period, plus accounting for the observed mean change only. And we can repeat the same thing, like generating thousands of hurricane seasons like the early period, but fixing the mean change, but only accounting for the higher moment change, like variance changes, skewness, kurtosis changes. And we can then compute return periods. How often we might expect an extreme season to occur, whether a 2014 quiescent period or a season like 2005. And this is what's shown here in the table for A's. So what we're doing here is we quantify the return period of a season like 2005, very extremely active season. And what we saw is that for the early period, this will occur only once every 267 plus minus years. So it's very rare for early period to shoot out a season like 2005, if you will. Now, if we account for just the mean trend, the mean change here, the return period becomes smaller, meaning the hurricane season like 2005 becomes more common. So it comes down to every 63 years. Now, if we account for only variance change, then it becomes even more common every 53 years. And for the recent period, both mean and variance changes, it becomes very common once every 23 years. We can do the same thing for the very quiescent season like 2014. It was very inactive. And you see that the return period was once every 3 years back from 1970 to 1994. It becomes a little bit more rare if we account just for the changes in the mean, because there's an upward trend. But then it becomes very common if we only account for variance changes. And then it becomes slightly less common if we account for the mean and the variance changes. We do the same thing for the TC number, which you see in this picture already. This is just a time series of the number of tropical cyclones and the time series of its interannual variability. And this is again applying the same model, but now for the TC number. We see a very drastic change. So there's a very significant right shift in the mean TCs. As you can see here, is consistent with the upward trend in the number of TCs. But also we see a significant change in the distribution, like a broadening and more skewness of the distribution. And that is well explained by the increase in the variance. And you see here the returns period for each of them. So hurricanes like 2005, when it comes to a number of TCs, become very, very common in the recent period, if you account for both changes in the mean and variance. And here we show that changes in the mean give you a much common return period every 51 years compared to just changes in the upward trend. So for one every 114 years. So in summary, increases in the mean and interannual variability have had a compounding effect on the occurrence of active TC seasons and an opposing effect on the occurrence of inactive TC seasons. So the question is the observed increase in the interannual variability and thus the occurrence of extreme active and inactive TC seasons project to continue into the future under anthropogenic climate change? To answer this question, we'll rely on computer models, on climate models. And for this part, we will concentrate on high-resolution model intercomparison project, which is basically a CMIS6 archive that follows the same CMIS6 protocol, but the only difference is that these models are a little bit higher resolution in the horizontal for the atmosphere, so they can reproduce hurricane activity with greater fidelity. And this archive consists of two scenarios: one a historical period from 1950 to 2014, and one for the future projections 2015 to 2050 under the most pessimistic emission scenario, which is the SSP 585. Here is a list of the models that we use, and in total we use around 20, I think it's around 20 models, and there are in total 87 ensembles because some of the models have multi-ensembles. So we use all of them. Some of them are slightly low resolution, others are high resolutions. And then we use the way we detect hurricanes and tropical cyclones here are using a tracking algorithm. Because tracking algorithm is model dependent, is parameter dependent, we rely on two tracking algorithms, which are very distinct. One is here called TRACK, and which detects tropical cyclone by identifying vorticity features and accounting for a warm core criteria. And then we use also tempest streams algorithm that accounts for sea level pressure depressions as well as warm core criteria. And these two algorithms, more details on that are presented in Roberts et al. Here is just, this is a very busy plot, but I'll walk you through it. On the bottom row, these are all reanalysis, and the top two rows are the models. And what it shows is basically a model evaluation. On the bottom right is hurricanes and tropical cyclone activities globally from true observation from the IB track, whereas the others are reanalysis products. And the numbers in the middle, here in the center of the pies, represent the mean number of tropical cyclones per hemisphere, northern hemisphere, southern hemisphere. And the pies, the actual slides, represent the percentage or proportions of TCs for each subbasin. I just want you to concentrate here on the northwest slide here that says NA, that means North Atlantic. So in observation, about 21% of the cyclones occurs in the North Atlantic. And you can see that for all these models, this is fairly well represented, although some of the models do have very little tropical cyclones. And most models, including the reanalysis, have too many tropical cyclones in the southern hemisphere. So this number here in the bottom is too high compared to the true observations. But overall, the models do fall in line fairly well with the reanalysis, and somewhat well, depending on the parameters that have been measured with the true observations. But especially for the North Atlantic, about 17 to 21% of the storms occurs in that basin. So that's well represented there. So a question is the observed upward trend in the interannual variability also well represented in these models? So what I'm showing you here is just a scatter diagram of ACE variance trend in the as the horizontal axis versus TC number variance trends in the vertical axis. And here, this is from observation. You've seen this plot already. There's an upward trend in the number of TC interannual variability, if you will. And also there's an upward trend in the interannual variability of ACE from observations, which is about 4.35 units of ACE as a trend. And that's represented here by this dot. Each black open dot here represent each of the 87 ensembles from the high resolution models. And you can see that there's a good scatter, but overall, there's more models that lie on the upper right quadrant, which is the quadrant that agrees with the observations. Although most of the models here underpredict and underrepresent these trends, with lower trends in both the ACE values, but especially in the TC number. But this is the multi-model mean. It's also in the upper right quadrant. So again, most of these models, 49 out of 87, are in the correct quadrant, whereas only 6 models says that there's a reduction in ACE compared to an increase in the TC number. And this is what the numbers show on each of the corners. Now, this is only for the observational period, 1970 to 2021. What about the future? What does this model says in the future? Here, what I'm showing you is all the models, and what we did was we computed the variance ratio, 21st century variance versus 20th century variance. And here, 21st century is defined as 2020 to 2049, this 30-year period, and the 20th century is defined as the 1950 to 1979 period. The dots in red are increased variance in the future. The dots in blue are reduced variance in the future. And here one represents, the line 1 here represents this equal variance. So there's no change in the interannual variability in the future. And the top panel is for ACE, and the bottom panel is for the number of TCs. So as you can see, there is a, and by the way, this in black here are the multi-model mean. And also I'm highlighting that we use 2 detection algorithms, which give you kind of like a distinct perspective of what's occurring. So both, if we use either detection algorithm, show that there's about a 58 to 64% variance increase in the future when it comes to accumulated cyclone energy compared to the 20th century. Whereas for the TC number, there's around 15 to 49% increase in the interannual variability of TC activity, accounting for all these models. So now we're going to shift slightly gear a little bit, and I want to show you, instead of a time series, I want to show you where these changes will happen. And but before we do that, I first want to mention overall changes in the mean activity in these models. So you can see that in this paper from Becky and Knudson 2008, they show a very nice inhomogeneous dipole-like spatial pattern of TC activity changes. And there has been several work arguing that the increased TC activity in the interior of the basin here in the central and eastern portion of the Atlantic is mostly due to trends in the observing system. So it was very likely that you miss a storm here in this interior, whereas it's very unlikely that you miss a storm here in the Caribbean or Gulf of Mexico because it was going to impact someone. So always a question whether this is natural driven, this is anthropogenic, or is this really an artificial trend because of the observing system and the data quality. We repeat similar analysis using the high resolution models. And of course, there's no issue with data missing here. All data are equally represented. And we see the same structure in the mean changes, future versus present. So we see an enhanced TC activity as measured by the track density here every 5 degrees over the interior, and a reduction over the Caribbean. Now, there has been papers like Liu et al. 2017 that argue that this is due to more TC genesis in this location here over Cape Verde region and well into the MDR, east of the MDR, and fewer TC genesis here over the Caribbean, and also enhanced SSTs and reduced wind shear here over the interior, which shift the TC genesis eastward. And that's what we exactly see here when we look at the changes in the TC genesis. We see enhanced TC genesis over the eastern portion of the basin and reduced TC genesis over the Caribbean. Now, the question is, how does that match with changes in the interannual variability, which is the main scope of this talk? Here on the left, this is exactly the same picture I showed you before, changes in the mean for track density versus genesis. And on the right is variability changes in track density and genesis changes, interannual variability. As you can see here, for at least for the track density, the interannual variability changes is fairly homogeneous. We don't see the dipole. And also it's fairly large. Note that the color scale are equal compared to the mean changes. So interannual variability changes is as important, if not more important, than mean changes, especially if you average throughout the basin. But you can see here more interannual variability of track density for most of the basin. For the genesis, this is even more striking. Although the spatial pattern looks similar, changes in the mean versus changes in the variance, the changes in the variance is much larger than changes in the mean genesis, where we see more interannual variability, significantly more interannual variability of genesis activity here in the eastern portion of the basin of Cape Verde Island, for example. So all this will argue for more extreme swings between an active season and an inactive season in the future, which highlights the importance of variance changes. We also look at CIMI-6 future projections. These are lower resolution models, but the target here was to look at large-scale drivers, like large-scale wind shear, large-scale atmospheric stability, and changes in the global SSTs, for example. So, and also the motivation here to bring in CIMI-6, besides the high-resolution MIPS, is that we have more data and longer period. We can extend this all the way to 2100. So this CIMI-6 work that I'm showing you now is complemental of the high-resolution MIP that I already shown you earlier. So the question here is, does the projected increase in the TC variance coincide with an enhanced large-scale ocean atmospheric variability enhancement? And the answer looks to be yes. This is for several CIMI-6 models. We computed the variance ratio of interannual variability of vertical wind shear. And as you can see here, there's about a 50%. 1.5 represents 50% here. 1 means equal variance between 20th century and 21st century. So there is about a 50% increase for some regions here of internal variability of vertical wind shear. Similarly, there's about a 40% increase in the lifted index. Lifted index here is used as a proxy for atmospheric stability, which is relevant for deep convection. And then E coincides with the wind shear increasing the variance over the main developing region, and coincides with the result we see already with ACE, for example, that is projected to increase by about 50% its interannual variability. We also look at SSTs, how it would change in the future. The top panel here is just the regression of sea surface temperature with hurricane activity over the Atlantic. So warm NDR and cold tropical Pacific is conducive for more active hurricane season, at least when it comes to ACE. Now, the bottom plot is the variance ratio of the future versus present sea surface temperatures from CIMIC 6. And you can see that, for example, consistent with the earlier work, Lopez et al. 2022, that I showed you, that ENSO El Nino is projected to be larger amplitude and growth at a faster pace, especially in the Central Pacific here. This is consistent with that notion that there's enhanced variability over the tropical Pacific, as well as a very large enhanced variability over the tropical Atlantic, which corresponds very well with enhanced variability in TC activity, especially in the interannual timescales. So we're going to use SST, as I promised you earlier in the talk. We're going to use this SST index, interbasing index, that's already been used today to forecast hurricane activities. We're going to use that in the context of CIMIC 6 and look at the future projections of this index. And that's what we did here. This is just from West et al. Showing how well this interbasing SST index simulates accumulated cyclone energy in the Atlantic. It has a very good 0.6 correlation from observations. So we're going to use this index. Basically, it's NDR minus Nino 3. So this is the ideal pattern for an active hurricane season. And we're going to project that into the future using all CIMIC 6 models that I've shown you earlier. And we're going to look at the likelihood of active, inactive, and near normal seasons. And that's what I'm showing you here on the right. So this is just a time series here from 1920 to 2080 of this interbasing SST index, which mimics, or we can use it as a proxy for hurricane activity. And we computed what is the likelihood of having an active, inactive, or near normal season. And for the 20th century, we use the 20th century parameters. We define active season based on 20th century thresholds. So what you can see here is that the green here shows it goes down, meaning near normal seasons will become less common in the future, at the expenses of more common above normal seasons in red and below normal seasons in blue. And the expected value here is 1/3. So we expect, based on the definition, that they have equal chances of occurring. Not so much in the future if we fix this threshold for the 20th century statistics. And we can even compute what is called time of emergence, where we might expect anthropogenic signal to emerge on top of the natural variability. And it's somewhere around this decade where we see enough reduction of the near normal hurricane seasons that it lies well below the expected value. So this suggests that the anthropogenic signal, when it comes to interannual TC activity, has already emerged on top of the natural variability. We can do something similar and in comparison using the actual simulated storms in the high resolution models. So what we did was we computed the PDFs, and here on the left you've seen this already. This is from the CIMIC 6 proxy. This is from the high-res MIP 21st century versus 20th century distributions of above normal, near normal, and below normal. And you can see a very similar pattern where the distribution of near normal goes well below the expected value of 1/3. So it comes to only about 24% likelihood of occurring in the future climate compared to the present climate. Whereas the above normal becomes very common at a 38%. This is well away from the 1/3 or 33.3% probability of occurrence. So this is matched pretty well with the SST proxies and the notion that future internal variability increase will enhance the distribution of TC activity, conducing more active hurricane season to occur. Now, this has some implications. One of the implications is we can look at cause and effect, for example, and what is, for example, the changes in this PDF of seasonal TC activity will give you more insight on what might we expect in the future. And then we can use cause counterfactual theory to assess whether climate change is a necessary condition for more active hurricane seasons in the future. So this is what we're going to do now. And what do I mean by that? I was thinking about how to explain this better, but I think this is a diagram speaks much better than myself. So this is what I do. Is first, imagine two words. One is a pre-industrial word. We're going to call that counterfactual word. And for the purpose of this talk, this is 20th century. And then we're going to call factual word the 21st century. And cause and effect is nothing more than just what is driving an effect to occur. For example, in the counterfactual word, we can assume for the purpose of this talk is that we only have one cause, represented here by Z0, where Z0 is just our baseline of pre-industrial 20th century, and the effect will be a hurricane season. Now, if you introduce external forcing, external factors like anthropogenic climate change, we can call it C1 here. And depending on how they interact, C1 and Z0 will give you a different effect. For example, here, Z0 and C1 are necessary conditions for E to occur, the event to occur. Whereas here, Z0 and C1 are just sufficient conditions for the event to occur. And on the extreme right, C1, let's say anthropogenic causes, are necessary and sufficient conditions for the event to occur. Now, when dealing with extreme weather, like hurricanes, and extreme hurricane seasons, like those that lies at the very end of the PDFs, only talking about necessary condition matters, because it's very difficult for, let's say, anthropogenic effect, and very unlikely to be the only cause of a very extreme hurricane season. So here, what we talk about is anthropogenic effect a necessary condition for a hurricane season to occur? And if it is, what is its relative role relative to natural causes? So we're going to compare these two words, where here is 20th century, only natural, versus 21st century, only natural plus anthropogenic. And we can compute what is known as a probability of necessary causation, where it's just a ratio of probability as a function of an event occurring. And we're going to define this event as a very extreme hurricane season, like 2005, for example. So you can think of P0 being the probability of an event occurring in the counterfactual world without anthropogenic effect, so here. Whereas P1 is the probability of the same event occurring in the factual world with anthropogenic effect here. So we're going to compute these two probabilities using the Markov model I presented earlier in the talk. And we're going to use 1970 to 1999 for Z0, and then 2020 and 2049 for Z0 and C1. And we're going to use all 87 high-resolution models to compute this probability of necessary causation. So the question is whether C1 is necessary and by how much. And this is what is shown here. I'm sorry for the amount of words in this slide, but this is a very complicated plot. So on the x-axis, I'm showing you different values of accumulated cyclone energy. And for reference, the most extreme values, 245 units, occurs on 2005. So this is the dashed vertical line here. On the vertical, what I'm showing you is just probabilities. Basically, probability of necessary causation from 0 to 100. And I outline here a few color beams for representation. For example, very unlikely, probability of less than 10%. And these are follow the IPCC terminology. And of course, very likely probabilities are probabilities higher than 90%. The red line here is the function of the probability of necessary causation as a function of accumulated cyclone energy. And the whiskers are the uncertainty range by randomly selecting 40 out of 87 high-resolution models. And what we show here is basically pay attention to the intersection between the red line and the vertical dashed line here. So this vertical dashed line is the ACE similar to the highest ACE we've seen in the observation 2005. What is the likelihood of a hurricane season like 2005 to occur thanks to anthropogenic effect? So based on this analysis is a 91% likelihood that anthropogenic effect was a necessary cause for this hurricane season to occur, with a confidence interval between 73 and 95%. So overall, anthropogenic effect has increased the likelihood of 2005-like hurricane season by 11 times over the 20th century period. So this suggests that anthropogenic effect will very likely be a necessary condition for events like that to occur. And mostly because there's a broadening of the distribution. There's not only an upward trend thus far in the Atlantic, but also there's a very distinct and strong upward trend in the interannual variability. So in summary, most of the literature assess the role of anthropogenic forcing from mean changes perspective, like TC frequency, landfalling. This work demonstrates that interannual variability changes has played a dominant role in determining the occurrence of both extremely active and extremely inactive hurricane seasons since 1995. And increases in the mean and interannual variability have had a compounding effect on the occurrence of hurricane seasons. And that it is also shown here based on future projections from the high-resolution models as well as the CIMI-6 models, that the internal variability of Atlantic TC activity is projected to increase by a significant amount, around 60% for ACE and between 15 and 49% for the TC number, which all this will lead to a likely hyperactive hurricane season. And in summary, also I want to mention the implications for the seasonal outlook is that future intensification in the variability of Atlantic TC activity will result in more wild stream swings between an active and an inactive hurricane season. And that these are driven by well-known large-scale climate factors like ENSO and Atlantic SSTs. So the good thing is that we can predict those with some fidelity right now. So we might expect enhanced predictability in the future, assuming nothing else changes. So hopefully this will lead to improved probabilistic seasonal outlook for TC activity. And with that, I'll stop and take questions. Thank you.